All right, if you don't mind, we're going to get going. I'm going to like to welcome everyone to another installment of our Lunch and Learn webinar series. Everyone should be muted when you log on. I'll ask you to remain on mute, please, until the end of the presentation, when we will open it up for questions. There's also a Q&A function and a chat function. I'll keep an eye on that. If you want to go ahead and type in questions and comments as you think of them, please do so. This session is being recorded, and the link to the recording and the slide presentation will be provided to everyone who signed up for the webinar, and it will also be available on demand to any NEBRA members unable to attend. So again, thanks for joining us today to learn about high temperature pyrolysis for biosolids and what happens to PFAS in the process from NEBRA member Char Technologies. I am very pleased today to have both Andrew White and Andrew Friedenthal with us here today, although they're calling from the left coast, and I'm hoping the transmission will be uneventful today. So Andrew White is the co-founder and CEO of Char Technologies. He has a master's degree in chemical engineering from the University of Toronto. And after a eureka moment in the lab, launched Char Technologies. He's also has a master's degree in business entrepreneurship and technology from the University of Waterloo. And he has won the IBK Capital Ivy Business Plan Competition, been named the OBBA's Young Entrepreneur of the Year, and led Char to be named the CIX Top 20 Most Innovative Public Companies. Andrew leads by example, providing clients and staff alike with clear guidance and actionable insights that help make our world a better place. And Andrew Friedenthal is the business development manager for CharTech Solutions. He has an arts degree from McGill University and is proficient at Mandarin with his HSK 5 certification. He has international experience conducting business in China, the US, and Canada, while working across different sectors, including technology, plastics, and organics, to achieve leading edge and sustainable products from multinational organizations. Andrew is incredibly passionate about driving sustainable growth, helping clients eliminate pollution by developing innovative solutions that deliver long-term value. Pretty typical NEBRA members, very passionate and excited to talk about what they do. And that is the best thing about NEBRA, our members, and the challenging work you do and your willingness to share with all of us. And with that, I'd like to ask Andrew and Andrew to go ahead and unmute and take it away. We're very excited to hear about your technology.
For sure, and we're excited to be here. And it looks like Andrew Friedenthal dropped off because of poor connections, which is why I dialed in as well as the backup here. So it's Andrew White here, and I'll take everyone through the presentation here. I'm not sharing my screen because I'm dialed in away from Wi-Fi. So just to make sure we don't run into any connection issues. So if we can move to the next slide, I can see the slides here as well. So to give you the quick overview of who Char Technologies is, we have three operating groups. The first is Alltech Environmental Consulting. And within Alltech, it's a lot of engineering services, compliance work, air emissions, property due diligence, that type of environmental engineering work. CharTech Solutions is our EPCM group. We have two primary technologies. We do industrial clean water systems, so things like MBRs and RO systems. But the second bullet here, waste reduction, renewable energy, that's our high temperature pyrolysis, and that's our big market opportunity, and also what we're here to talk to you all about today. And then third is Char Biocarbon. That will make sense probably a little bit more as we get through the presentation, but as one of the outputs of pyrolysis is a biocarbon. This group is where we do ongoing R&D to find the highest value applications for that biocarbon. And that's also the group that will be the off-taker, if needed, for a high temperature pyrolysis project. So next slide, please. So here's some reference installations just quickly. The first one on the left is our demonstration facility in London, Ontario, which we're running daily. The middle is just an RO plant, and then the one on the right is an MBR. The only reason we like to point that one out is we installed that to treat effluent from a apple juice and cider manufacturer, such that the water could be reused within the facility and met food regulations for that. And Coca-Cola installed a similar system about 2 years after we installed ours, and Coke claimed they were the first, but if they claim they were the first, we know we were 2 years earlier. We just had a slightly smaller marketing budget than Coca-Cola. Next slide, please. And of course, this is a bit of a general presentation, so I probably don't have to get too in-depth as to some of the challenges with the land application of biosolids and digestate. Digestate for us is the solid fraction left over after food waste, source separated organics, anaerobic digestion facility, which we also do a lot of work in. So we'll kind of maybe get straight to the technology, and we don't need to discuss these challenges because I'm sure everyone on the call is well aware of it. So next slide, please. So this is the graphical representation of high temperature pyrolysis. And you can see at the bottom of this graphic, we have three distinct feedstocks. So one is biosolids. The second, as I mentioned, is digestate and compost, so the residuals from those organic waste to energy facilities. And third is wood and agriculture. And so we identify each one separately because while the kiln is the same, so it's the same kiln that operates at high temperature, and I'll talk a little bit more about that in the next slide, but it's the same kiln, but depending on what you put in it and what temperatures you run at, you get different outputs. So you're always getting clean energy and biocarbon, but depending on the feedstock and some of the operating conditions, you can either produce more energy or more carbon. You can produce higher hydrogen contents in your gas or lower hydrogen contents in your gas. And specific for biosolids, and probably one of the biggest benefits of the technology is the ability to destroy all of the PFAS compounds, at least the 28 standard ones we test for, as I'll get into a little later, we are eliminating from the solid stream. Just to talk a little bit more about that first bullet, renewable natural gas, that's from that wood stream. Green hydrogen, we announced a project a couple months ago now with Hitachi, Zozan, and Nova in San Luis Obispo, California, where we are processing their digestate. So it's that kind of relatively high moisture content, solid compost material. And that plant is processing 18,000 tons of digestate a year, or will be once it's commissioned in the summer. And we'll be producing 1.3 million kilograms of green hydrogen a year. So obviously we're very excited about that project as well. Next slide, please. So this is what our high temperature pyrolysis facility looks like. So to kind of walk you through a little bit, what we're looking at here is actually where the mouse is, that red motor on the back. You see a little circular disc and then a larger silver plate. So that's the heat tube. So inside of the kiln, we have a heat tube. If you look at the far end of the box, you see a bucket elevator kind of coming up and down. And at the bottom of that bucket elevator, there's kind of a yellow box. So that's our airlock. So basically what's happening here is at the front end where that large roll-up door is, we're receiving material. It's going into our loading hopper. It's going up the elevator through this airlock. And this airlock is keeping all the oxygen out of the kiln. The material then goes through this heat tube from the far end of the picture to the near end. And the heat tube rotates, and then inside the box is where we have the burner package. So you see kind of three gray boxes along the side. Those are them. Yeah, those are each of the burner management modules. So we're heating the heat tube up completely externally. So it's not gasification where you're putting in a little bit of oxygen. It is pyrolysis where there is no oxygen in the system. And then what we're looking at the back end is the material, the now biocarbon, falls out the bottom and goes through that first screw. That's a cooling screw. There's actually 2 more cooling screws to bring the temperature down, and then it deposits in that white tote bag hanging there. And then the syngas comes out of the duct at the top right of that end plate, and that's where it can be treated. Some of that is returned back to the burners, and the rest, if the moisture content on the biosolids is low enough, is something that can be captured as additional energy. Next slide, please. And this is a build one, so we're gonna I'm gonna have to keep saying next one, but that's okay because I don't want to give away the punchline too soon. So what I did here is just a box diagram of kind of the main process steps. So, assuming we're getting biosolids that have gone through, depending on the facility, a screw press or a centrifuge or some type of dewatering, and brought down to about 83% moisture. At that point, we do still want to dry it down before it gets into the kiln system. So we have provided and can provide a dryer. There's lots of people who have preference on dryer types, and we're fine to work with other dryers. The only caveat is that we want if it's a third-party dryer, we want it to be able to be run off of syngas. So it has to have a burner package that can take syngas. Next box, please. So once we go out of the dryer, in this case, what we're showing is a case where we were drying it down to 10%. And the reason in this exact case we were drying it to 10% is the site wanted the flexibility of saying, if the kiln is offline for maintenance, or maybe there is a market opportunity for dried biosolids, they wanted the dryer package to be able to get it to that really less than 10% moisture content requirement. If we know we're just running it through the kiln and we don't want that alternative of dried biosolid pellets, we can take, at this stage after the dryer, about 36% moisture because our kiln system can have a waste heat recovery pre-dryer to get it down. We're happy taking material into the kiln at 20% moisture. The most efficient place to be is around 15 to 20% moisture, but you have to balance that with CapEx, and at times we can get up to 50% moisture into the kiln, and it'll still operate pretty reasonably. And that's a big distinction between gasification, because it's heated by the syngas externally, whereas a gasifier, you're putting a little bit of oxygen in to combust some of the biosolids that are going in. We can manage a pretty variable input on moisture content because, like we said, we're not relying on that material burning or smoldering inside the system to generate the heat. We're heating it completely externally. If you want to go to the next box, please. So the syngas coming out, and now you can start to see some of the mass balance of, we've got that 945 coming in, sort of where the biocarbons go, where the syngas goes. And then after gas scrubbing, if we go to one more box, we've got that water coming out that's still remaining in the material. And then we're producing, this relatively clean syngas. And if we go one more, I can show you why we chose specifically this 83% moisture content example, and that's kind of in this case, the break-even number. So if we had any higher than 83% moisture, we'd have to add some external energy to bring that moisture content down. If we were getting biosolids at 75% moisture, we would be generating excess syngas that could be sent to a genset. It can go into, like a Jenbacher or a CAT to make electricity. Or we could look at extracting hydrogen as that market develops. So that's a pretty high level box flow of kind of where the energy is going and where it's being created, where the mass is going and where it's being created. Next slide, please. And so again, this is the system. As we talked about, it has that high mass reduction, and the key point I want to reiterate with this slide is that the energy generation, and that is up to that 83% moisture content, we're generating enough pyrolysis syngas to run the system, to be autothermal. So it can handle some pretty high moisture contents. Now, we're obviously not generating energy to sell outside of the system at that high moisture content, but the point is it can operate without any external energy. And the drier it is, the more energy we're able to make for export. And just a quick note on the bottom here, these are two of the potential product streams that we have patents on. Sulfur-Char is an activated carbon, clean fire is a carbon neutral coal replacement. Now, in general, clean fire has got to be made from things like wood because it has much lower ash content, but sulfur-char and some of the other advanced biocarbons we're working on can be made from the biosolids. Next slide, please. So this again, I'm going to talk a little bit more now about why high temperature pyrolysis versus more standard pyrolysis is so important. And this is the first example of that. And that is, we don't really want this orange stream. So this orange stream called condensate has two fractions. One is water content that's still left, and the other is bio oil, which if anyone on the webinar this morning or at this noon hour has looked at, it isn't great stuff. I mean, you have very clean feedstock streams like wood that struggle to market bio oil, so we want to get rid of that. And one of the ways to get rid of that is to run at higher temperature. And you can see what's happening at these higher temperatures is a lot of that oil, instead of coming out as oil, is coming out as gas. And that's important. And that's how we can get these high moisture contents into the plant in the first place and still be energy self-sufficient because of that ability to create significantly more syngas than at the lower temperatures. Next slide, please. Just an example of some of the variabilities in syngas composition, but the important point here is one, the hydrogen component. So as the hydrogen economy takes off and people want hydrogen, right now it's really still isolated to California, but as we see demand for hydrogen, it is something that's extractable. The other is just to show that there is a fair bit of energy left in the gas in the form of hydrogen, carbon monoxide, methane, and other HC as other hydrocarbons. So things like C2, C3s, C4s, so propene, butene, ethene, that type of thing. Next slide, please. And so now I want to talk a little bit about some of the outputs and what some of their values are. So in this case, you can see we're making a product out of the digestate. And by controlling the conditions under which we process the digestate, we can actually make an activated carbon. And not only does it work as an activated carbon to clean sulfur out of gas streams, once it's saturated, we can use it as a fertilizer. So that little picture there is some growth trials we did at the University of Guelph in Ontario, where obviously the sulfur-char is that nice big corn plant on the left, and the control with commercial fertilizer at the same sulfur loading is there on the right. So it shows there is an ability to continue to extract value from the biocarbon depending on how we process it and what it's made of. Next slide, please. And again, on the just straight use as a fertilizer, there's an important distinction that I think people sometimes miss when we're looking at biochars and their applicability, and that is the available components. So often, even if you looked at the analysis from our biocarbons, you would see higher phosphorus than 5%. You'd see higher potassium than 0.5%. But it's really important to understand what's available to the plants, because often it does get bound up with some of those other components. So there is available phosphorus and available potassium and available nitrogen in the biochars, but just something when we're looking at biochar and its applicability as a soil amendment with fertilizer value, we need to make sure we're looking at the available and the soluble numbers and not just the total ash, because those will be two different numbers. Next slide, please. And on the output, of course, the other really important piece is the destruction and elimination of PFAS. So because we're doing this work with a number of different clients, and generally PFAS and biosolids is still something that is not something everyone wants to disclose. We're kind of aggregating data here so that it's not easily identifiable. But the important point here is that if we had 100% PFAS, and this is the 28, so it has PFOA, PFAS, all the big ones in there. If there's 100% remaining in the biosolids, most of it is gone at 500 degrees Celsius, which is where a standard pyrolysis plant operates at, but there is still residual there. Once we get into the 700, 800 degrees Celsius range, it's all gone. And if you want to just hit next, I think we've got a little bit of a build out on this one as well. Yeah, so at 500, what we see present, we do see PFOA present. And not only do we see it there, we see its concentration increasing slightly. And so what that's telling us is that at 500 degrees, we're not really liberating it from the material coming in. And the reason the concentration increases is because we are losing mass from the solids. So we might have the exact same mass of PFOA, but because the overall solid mass is dropping, its concentration is increasing at that 500. And next bullet point is, of course, at 700, we saw all of it was eliminated. And now we did one of these studies in conjunction with Jacobs, and they've presented this data at a few conferences as well. And they validated with us that, yeah, at the 700 degree plus range, we are getting rid of all the PFAS in the solid stream. Next slide, please. And so where is it all going? And the point that I'd like to make here is that it's all gone at 700 from the biochar. It's all gone. It doesn't come out and condensate at any temperature. But at that 500 degrees, there is still an appreciable amount in the syngas. Once we get into the 700 degree range, there's much, much less left in that syngas. And that, of course, would need to be scrubbed out and dealt with appropriately. But if you're dealing with a much lower concentration, that becomes a little less burdensome. And it's really important to understand where the PFAS is going, how much of it is remaining, and how much of it is really being cracked and destroyed into more constituent parts. Next slide, please. And that's it. So thank you, everyone, for the opportunity this morning and to be able to present our take on high temperature pyrolysis. And I am looking forward to the questions.
Okay, thank you, Andrew. I'm going to stop sharing my screen so we can get the full thing. And we do have some questions coming in. And what I'm going to suggest is I'll take care of the first couple, but if you would like to, you can go, you can raise your hand and I'll just call on you. You should be able to unmute. All right, so the first question, Andrew, was just looking for a little bit more detail or further description of the feedstock in the California installation, and does it include biosolids?
Yeah, the California one is not a biosolids case, so it is from an anaerobic digestion system, but it's fed with food waste and urban forestry, leaf and yard waste, sticks, that type of thing. So all of the biosolids work that we've done at scale has been in London. So that is a specific facility that is being built on the back end of Hitachi Zosen and Nova's plant.
Okay, thank you. Another question is, does your process handle unstabilized sludge as a feedstock?
Yeah, I mean, The answer is yes, with the kind of caveats, and the two caveats are, one, we need to make sure we're still able to get, when we're talking about does it handle it, it still needs to go through a drying process. So we put it through the dryer, we're able to control odors and emissions through the drying process, then yes, and in fact, the less processed it is, the more net energy we can make, provided that it is dried before it goes into the kiln. Because as you take it through additional process steps, let's say you take it through anaerobic digestion, you're losing some volatile matter through that process. And volatile matter is one of the things that converts to energy. So yes, with caveats. How's that? Just to make sure we're being careful.
Very good. A couple of questions on the syngas and the emissions. Where do the emissions from the dryer module go?
Yeah, and that certainly depends on whether it's a dryer that we're putting in or that a third party is providing. So we've scoped out systems with belt dryers, with drum dryers. We would put in, because of how we know how to build stuff, we put in a screw dryer, and so the emissions would be collected, condensed. As part of our system, which we don't show, we always have a thermal oxidizer, and that thermal oxidizer is designed to take the entirety of the syngas load. So let's say you're burning the syngas, and whether its end use all of a sudden shuts down, or someone inadvertently closes a valve, or something happens, all of that gas can be directed to the oxidizer for destruction. So off the dryer, after condensing, the remaining air from the dryer can go through the oxidizer if we're in a odor concern area. And I think that's a great way to manage it, because we do and can put a lot of air through the oxidizer.
Thank you. When you burn the syngas, what temperature do you burn it at?
I mean, it's an interesting question, because it's one I've never been asked before. What I can tell you is we look at it more on a energy content basis. So by energy content, we're saying, how does it compare to natural gas? MMBTU per pound, that type of thing. And I'm gonna have to apologize, because I'm gonna have to switch to my Canadian units just for a moment, but we can convert later, hopefully. But to give you an example, natural gas is about 50 megajoules per kilogram, so energy per weight. So a kilogram of natural gas has 50 megajoules. A kilogram of syngas has between 18 and 20. So it is a lower energy gas than a natural gas, but if you have the right burner package, you can burn it in a similar fashion.
Thank you. If that didn't answer your question, Mike, you can raise your hand again. I've got a couple questions through the chat for you, Andrew. This one's from Eric Spargimino, the residuals chair for NEBRA. He said he heard recently, and he has no backup for it, that pyrolysis requires indirect drying upstream and could not utilize direct drying. Is that true? And if so, why?
I don't believe that's true.
That's why we always check.
Yeah, I'm just trying to speculate maybe why you would have heard that, or why some systems would ask for that. But our system, our airlock is between the dryer and the kiln. So any type of dryer that's been used or could be used to dry biosolids under any circumstance can be used with the pyrolysis kiln, because all we're after is how dry it is. So like I said, the only pieces that we would want to make sure that that specific dryer could use syngas in some way, shape, or form, so that we're being more energy efficient. So, when we look at things like belt dryers, it's a little bit different than maybe a direct dryer, and perhaps that means the energy available in the material changes. if it's using a direct dryer, but I can't say I know for sure. I'll have to think about that one. But we generally are looking at what does the material going into the kiln look like. That's where we do the energy and mass balances, and then we can work backwards and say what's the most effective way to use the energy we're making to ensure we're drying, and ideally making more energy if the balances are there.
I told you would get some good questions.
Absolutely.
Presenting to NEBRA members. There's some more in the chat here. With the remaining PFAS converted into the syngas stream, are you anticipating the possible future need to provide scrubbers on air stacks?
Yeah, so the syngas, the way it works now is that we go out of the kiln, we go through basically a condensing open spray tower to bring the temperature of the gas down. We go through a scrubber and a polisher. And really what we're doing in a more traditional, let's say we're running wood, is taking out any aerosolized oils, because we don't want that in our gas just in general. We're taking out any carbon dust that could carry through, and we're taking out any contaminants. So when we run things like digestate, we're going to get a little bit of H2S, so we need to scrub that out as well. We then have a dehumidifier and an activated carbon guard bed to make sure the syngas is clean. And so the idea is we are cleaning the gas before it's being combusted, so that what you're getting out of the stack is emissions from clean gas being burned. So, similar to what you'd find in a natural gas burner versus burning this syngas that has a little bit of PFAS. All that fluorine's gone somewhere, so it's likely gone to HF and other fluorine molecules, which are scrubbable, but then you burn it and you've got fluorine in your stack gas. So that's our approach, is let's clean it before it's combusted, so we don't have to worry about all the weirdo complex products of combustion that you could get by burning a more complex syngas.
Thank you. And if there's I believe, do you have a white paper, Andrew, that you could share with me that I could follow up with the group on regarding the PFAS testing that you've done?
Absolutely, yeah, and we keep growing that library as we keep doing more and more work on it.
Yeah, I think that'd be great to share with folks afterwards. More questions coming in. Someone's asking if you have a list you can share of your ongoing or past pilot studies or full-scale installations with sludge only.
Yeah, so to your question about white papers, we can share more details on those demonstrations for sure.
Okay, that'll be included in that too. We'll get you that, Eric. Oh, here's a good question, and then we do have other questions in the Q&A. This looks like the last one in the chat, but someone's asking you if you've seen, and hopefully you have, because I think I sent it to you at CHAR, the recent the advanced notice of proposed rulemaking from EPA regarding how or possible regulations of pyrolysis and gasification systems.
We have seen it. Thanks for asking, Eric, and making sure that we did see it. And we have a response being prepared for it. I believe it's due the second week in November, if I'm not mistaken. Might be the first week, but yeah, we have. Thank you.
Okay, very good. Especially since you're in Canada, we want to make sure you're right on top of that. All right, we got that one. All right, so here's a very practical question from one of our members. Do you have any cost data per dry ton for managing biosolids through this pyrolysis process of yours?
Per dry ton, the only reason I'm going to say no on this call is that there are some variables I just don't want to mislead. So I'm happy to talk about it in the context of understanding exactly what the biosolids look like coming in, where our scope is. Are we drying, or are we just taking the dried material? What's going on with the syngas? Is it waste activated sludge? Has it been anaerobically digested? They don't make a big difference, but I don't want to say the one and then say, well, it's for the other. So I'm certainly happy to talk about that with just a tiny bit more detail on what those things look like, and I'm happy to chat offline with anyone about that.
All right, terrific. I know who asked the question. I can certainly connect you. Another question from our friends at National Grid on the energy density for the syngas being less than the natural gas and needing to accommodate the lower energy. Oh, I think he's just saying he got your answer now.
Awesome.
And that he gets it. If that's not correct, Mike, let me know. And then here's another from an engineering and air permitting standpoint. Do you have a library of emission factors? Things that we could use in modeling, like mass of pollutants per mass of solids fed?
Yeah, we have a general emissions inventory that can be used certainly for the initial modeling. We, again, want to make sure we understand any nuance of that specific biosolid stream. But we have the base library to do the majority of the work, and then I always like to test things, test the model. But yeah, to answer the question, we do.
All right. Yes, and just so you know, NEBRA is working on updating the BEAM model, which is Biosolids Emission Assessment model for calculating or estimating emissions from various biosolids management methods. So yeah, we'll be looking to make sure we have some data for these pyrolysis processes as well, as folks start deciding what their future is in biosolids.
Yeah, awesome.
All right, let me just check one more. All right, that is all the questions. Wait a minute. Nope, great presentation is the last question. I'll give one more 30 seconds or so here for additional questions, but if there are none, we're going to give you, there's a little bit more here. Here's another question, thanks. How large are your units' footprints? That's a good one, because
yeah, I
don't think that came up.
No, it's a great question. So the picture you saw of our London plant is in a building that is 20 feet by 40 feet. And that facility takes dried material, so it does not include a dryer, but that's the kiln, package, and the thermal oxidizer. And that's a facility that can process 1,100, if I did my conversion right, pounds per hour. Biosolids, our largest kiln size, can process 3.5 metric tons an hour. And that's on a dry basis, so that's going into the kiln. And again, without the dryer, but just the kiln package, would be at around 8,000 square feet for that larger size. And we basically have 3 different sizes: small, medium, large. And then if you need more than 3.5 dry tons per hour, we start to do the modular approach, where there'll be 2 kilns operating in parallel.
Okay. And a follow-on to that is, what's the maximum throughput, assuming 90% dry solids?
Yeah, so 3.5 metric tons per hour into the kiln at 90% dry. So obviously that increases as to what's going into the dryer.
Right. Okay. There's definitely a lot of interest in this. And yes, Andrew, we are rooting for you to have success with this process with respect to PFAS and still generating beneficial outputs.
We appreciate the support and the opportunity to talk a little bit more about it this morning here.
Yeah, and that'd be great if you could share the white paper with me. I will follow up with folks that have registered, and they can get a look at that as well. And your contact information will be there for some of the engineering folks who wanted to ask you more specific questions.
Fantastic. Looking forward to it.
All right. Again, thank you so much, Andrew. And Andrew, the other Andrew who disappeared. But good luck to you all. Again, thanks for presenting today, and thanks to everyone for joining us. This was the last session for the year, but we will be starting back up again in January, so watch for the announcement on the 2022 lineup soon. And I'm always looking for suggestions, so if there's something you'd like to lunch and learn about, please send me an email or call me, and I'll see if I can make that happen. All right, with that, take care, everyone. Have a great weekend.